Hi, I'm Nick Jester, and today I'll be explaining what is a derivative and what is its interpretation geometrically. So first of all, on the base, a derivative is the instantaneous rate of change of a function. So say we want to find the derivative at this point. We're going to say that's x, and the y value is f of x. The derivative at this point would just be the slope at this very point. Okay, and we'll say at this other point, it's a distance h from x, so we're going to say it's x plus h.
Thank you, Daddy.
And its y value is f of x plus h. Its derivative would be the slope again at this point, so it'd be like that, facing down. So the derivative here would be sideways, up would be upwards. So yeah, it's just the slope at any given point. But how do we find this? So first of all, what we want to think about is a secant line. So a secant line will basically tell us the slope between 2 points, like this formula. So if we take the secant line between these 2 points, we can see that it looks a little bit like this, just the line between them. But why is that important? Well, it's important because we can actually find the derivative using that. And what we do is we actually make it so that these 2 points are so close together that they're almost the same point. So how do we do this? What we're going to do is we're going to plug these points into this equation and take the limit as h approaches 0, or the distance. So we're going to do f of x plus h minus f of x over x plus h minus x. And as we can see, the x's cancel out, so we're left with f of x plus h minus f of x over h. And now we know h is the distance between these 2 points, so we want to find the secant line of these 2 points when they're super close next to each other. So what we actually do is we take the limit as the distance between them, h approaches 0, and this new secant line looks like that. So essentially the derivative calculates this slope at every single point on the graph. And that's what a derivative is and its interpretation geometrically.